3 of some fundamental chemical laws that are, laws that you don't really use moving forward in chemistry, but they kind of lay some foundational ideas. And the first one is conservation of mass. So conservation of mass is something, if you've taken a science class before, you've heard of it, right? It's this idea that mass cannot be created nor destroyed. Mass is just really any type of matter. So you can imagine, matter doesn't, like, you can't get matter out of nowhere. If you gotta make something, you gotta break it down and build it back up, that sort of thing. In chemistry, it comes, a lot of the biggest sort of example of conservation of mass is balancing equations, which is not something we've learned yet, but I guess I'll give you a little bit of an intro. A common type of chemical reaction is combustion, right? Fire, that's just a chemical reaction. And the way combustion works is you take some sort of, if you think about the fire triangle, it's like fuel, oxygen, and heat. You need fuel, so let's say we have propane, that's C3H8, and let's say we have some oxygen. After the combustion, you're gonna have some carbon dioxide, some water, and then your, energy, the light and heat that comes out of it. Here's the thing though, right? Mass in this case is through the form of these atoms, right? We know that, or we will learn in the next section, the book kind of goes backwards, but we know that atoms make up mass. So we want to make sure we have the same amount of atoms we end with as with which that we started with. Here we have 8 hydrogens. By the end of this, we're gonna have 2 hydrogens, right? Well, a good way to not like this is what happens. You end up getting 4, you get 4 times the molecules of water, right? So that way you end up with 8 times the oxygen, right? So for your input of fuel, you'll get 4 times the oxygen. But this is not fully balanced, because now we have, this is where it gets a little bit crazy. We have 2 oxygens and then 4 oxygens there. So we should probably put a 3 here, plus 3. But the thing is, we also kind of need 3 carbons here. I'm not going to go too much into balancing equations, because it doesn't really matter that much, frankly. But now we have 3 carbons there, and then if that balances that, and then that would give us 6. That would give us 6 oxygens plus 4 here, so that would be 10 in total, and then you get 5. We will come to learn a very systematic way to balance an equation. But these 5s and 3s and 4s, they kind of tell us the ratios. Like, I need 5 times the amount of oxygen gas in molecules, or then, it's like, it's like baking, right? My recipe calls for 1 cup of this and then 5 cups of this in order to get what I want. This ensures mass is conserved. So the next sort of law is definite proportions. So the law of definite proportions kind of just says that if you have a molecule, it's going to come in equal mass. So let's actually take a look at propane right here. Propane, in order to, make propane, you need 3 carbons and 8 hydrogens, right? So let's say we have, carbon has an atomic mass of 12 grams per mole, right? It's 12 AMU, which is really 12 grams per mole. And then hydrogen has, its mass is about pretty much 1 AMU, or 1 grams per mole. If you're unfamiliar with a mole, it's a mole is just it's sort of like a word for molecule, but like a lot of molecules. So it's like how a dozen means 12. So if I have a dozen eggs, that means I have 12 eggs. If I have a mole amount of molecules, I have 6 times 10 to the 23, 6.028 times 10 to the negative, times 10 to the 23 molecules. So a mole is just a certain amount of molecules. So if you give me 1 mole amount of carbon, it's gonna be 12 grams. If you give me 2 moles amount of 2 moles amount of carbon, it's going to be 24 grams. So that's just the idea of a mole. If we look, but you have, let's say we, you're going to have like the ratio of molecules is going to be 3 to 8, right? In order to make the propane, you need 3 carbons, 8 oxygens. So if we multiply this by 3, multiply this by 8, that means by mass, propane is, so by mass, that's the important part, it's 36 to 8, if I'm not mistaken, right? Because you have 3 carbons to 8 hydrogens, but the carbons are each 12, so it ends up being 36 to 8. So we could reduce this to, this will become, I think it'll become 18 to 4, and then you could even go this to 9 to 2. Yes, 9 to 2. That's actually, this is the ratio. So if you take propane and if you somehow are able to separate it and separate all of the carbons and weigh the carbon, separate out all the hydrogen and weigh the hydrogen, it should be a 9 to 2 ratio, right? No matter how much of the gas you have, right? If you have I think propane's a gas, right? No, maybe not. Maybe it's a liquid. Whatever. However much propane you have, right? It's always going to follow a 9 to 2 ratio, because if you have more carbon than oxygen, well, then you don't have propane. This doesn't follow our recipe, right? It's like if you're baking a cake and you have if the recipe calls for 1 to 1 and you have like 1 cup flour, 1 cup water, and you have 2 cups of flour, and 1 cup of water, then you don't have cake. Like, you're just not following the recipe, right? Every compound has to kind of follow its recipe, right? That's kind of the idea of definite proportions, and supports the idea of an atom, right? If you're telling me every compound has to follow a certain, like ratio of their elements by mass, well, that probably suggests that they're made of something very fundamental that can't be broken down, right? You can't break down, I guess, carbon more, so it has to be 9 to 2. The thinking is a little bit shaky about how definite proportion supports the idea of atomic theory, but multiple proportions definitely does. So the law of multiple proportions, it's a little bit wordy, but essentially you have to think about this. Let's say you had 1 gram of oxygen. With 1 gram of oxygen, let's say you want to figure out how much mass of nitrogen will combine with 1 gram of oxygen, right? So maybe for compound A, if we look at compound A right here, this is saying 1.75 grams of nitrogen will combine with oxygen. Compound B is saying, to form compound A, right? Compound B is saying 0.88 grams of nitrogen will combine with oxygen to form compound B, right? It's sort of like the ratios. Compound A, I guess, has a 1.75 to 1 ratio. I think that would be what? 7/4? Maybe 7/4 ratio, 0.88 to 1, right? That would form compound B. No, I don't think it's 7/4. I think it's a little bit different. I don't know, I could be wrong. And then for compound C, it's going to be 0.44 to 1, right? You need 0.44 grams of nitrogen to form compound C. But then what this law is saying is, well, hey, for compound B, it's just using twice as much nitrogen. From compound A to B, it's using twice as much as well. And then from compound C to B, C to A, that would obviously be times 4. So that's a very clean jump. And that kind of makes sense. Let's think about the things that could form, the molecules between nitrogen and oxygen. You could have N2O, you could have NO, and then you could have NO2, right? So let me just make sure that's correct. I think it should be correct, right? So this might not even be the correct, the way with how atoms bond, this might not even be the correct way, like how actual bonding would occur. But as you could see with this set of combinations, this kind of shows us that, well, this is like from nitrogen to oxygen, that's a 2-to-1 ratio, and then it grows 1-to-1, and then it grows 1-to-2. And, because we only have 1 gram of oxygen, we could like sort of make this side 1. So if this side is 1, let's make this side 1/2. So it's really a 1/2 to 1 ratio. 1-to-2 is the same thing as 1/2 to 1, if hopefully that makes sense. But hopefully you can kind of see, oh, this kind of illustrates what we have going on, right? NO, the compound B, right, it's going to be twice as much from the bottom, and then N2O is twice as much from there, and then we have a 4 times jump from NO2 to N2O. The ratios, not necessarily the ratios between nitrogen and oxygen, but the ratios here, right? From A to B, it's 2-to-1. From A to C, it's 4-to-1 in terms of nitrogen, right? It's this is a 2-to-1 ratio. This is a 4-to-1 ratio. From B to C, it's also 2-to-1. These ratios always deduce to clean whole numbers. And it once again supports the idea of atoms. If your molecules can only be made up of these discrete, like singular molecules, or not molecules, but atoms, right? Single particles, atoms, right? Well, your ratios are gonna have to conform to whole numbers, because you can't have, you can't like keep dividing up, right? You can't keep dividing up an atom into infinitesimally smaller pieces and then therefore get like irrational ratios. Hopefully that makes sense, right? If your atoms didn't have a stopping point and they kept getting smaller and smaller and smaller, these ratios would get crazy big and essentially irrational. But because we see in nature there are these ratios, we can kind of use that as sort of evidence that, oh, there has to be these fundamental building blocks of these molecules and compounds. So hopefully that made sense, and yeah, thank you for watching.